Yeah, because even if it's business, they don't get the police, wow. Yeah, he's like getting the Thursday before. Yeah, so he's like, there has to give
Okay, so we're going to move on to Chapter 5. And Chapter 5 is on project scheduling models. So I like this chapter because if you think about it, it doesn't matter what discipline you're in. You can be an engineer, you can be a financial consultant, you can be a wedding planner. Business deals with projects, right? Projects are temporary endeavors undertaken to get something done. Build a bridge, install a new software system, build a building, or refurbish a building. Those are projects. Okay, so very applicable skills to any discipline that you might have a career in. So we're going to talk specifically about something called project scheduling model. So not all of project management. There's a separate course in the MBA program called project management. I've taught that course in the past. I don't teach it anymore. But it deals with a lot of not just scheduling, but it also deals with things like risk and quality and human resources and all those good things. So let's kind of define some things that are important for the study of project scheduling. So first of all, a project is really just a collection of tasks that are done in a certain order. Sometimes it depends what you're looking at. Sometimes they call these tasks activities. But we're trying to get these things done, usually, if you think about terms of the course we're talking about, usually at a minimal time and at a minimal cost, right? So we want to get it done as fast as we can and as cheaply as we can. So our objectives of project scheduling are related to those things. We want to complete the project as early as possible, determining the early start and early finish time of each activity. We would like to also, we realize in a lot of cases that projects aren't always going to be known with certainty. When they built this building, they refurbished Schwab Hall, it took them about a year, and they said, there's a likelihood that we're done by this date might be 90%. The likelihood we're done by this date is only 50%. Because we know activities, when you do something, you're not always going to do it exactly in 5 days. You may say, 5 days is the average, but it may take 5 days plus or minus 2 days. So we want to build some variability, some variance into the project, and then we'll use probability to help us assess the likelihood of completion. We want to find the minimum cost schedule needed to complete the project by a certain date. We also are going to look at the results of possible delays. So as a project manager, you may have 100 or 1,000 activities in this project, and you're saying, well, we need to borrow some resources. Well, where can we borrow resources? Is it task 10 that we could actually borrow some resources from, put them on task 12, and still not delay the overall project? So we're going to look at that. We're going to look at possible delays. We're going to look at things like smoothing out resource allocation. So there are times in a project where they take more resources, but maybe my resources are static. Maybe I have 10 folks working on this project. So how can I move things around so those 10 folks are always busy? What tasks can I move up? What tasks can I move back? These are the things that we are going to be looking at. Okay. So I'm going to skip over this slide. So if we were doing a project, for example, cooking a pizza, and it's not a huge undertaking, but if we were cooking a pizza, we know there are activities or steps in that process. The first thing we do is we want to identify those tasks or activities. So that's the first thing. To determine optimal schedules for these activities, we first need to say, what are all the project's activities? And then furthermore, we need to put them into some kind of order, right? We know like putting the sauce on is an activity, but we know we do that before we put the cheese on the pizza, right? That's called a relationship. And we talk about precedence relationships among activities. Based on this information, we can go through the project and we can build a timeline. We can build an early start, early finish, a late start, and late finish for each of the activities. And I think the best way to do this is to look at a situation facing clone computers. Okay, so they manufacture Palm books or something, it doesn't really matter. But they have come up with, to get this project done, we need to complete these 10 activities. So, and they've grouped them roughly in manufacturing activities, training activities, and advertising activities. In an actual project, we probably have thousands of activities, not just 10 or maybe hundreds anyways. But we only have 10 here at this point. So we have those activities, we have descriptions for those activities. What do you think the next step is? So I know these are the activities I need to get done. In the business world, what do you think the next step is? I have these activities, what do I want to put with those activities? So I'm trying to figure out when this can be done. Go ahead. Resources. So one of the things that resources come down to is time, right? Duration. So we're talking about project scheduling. So one thing, cost obviously is one thing, but right now we're just going to focus on like the duration of activities. Does project A take 5 days, 10 days, 20 days, 50 days, 100 days, whatever it might be? Does project C take 1 day, 3 days, 9 days? It doesn't matter. So let's focus on duration. So we go down those activities and we assign durations to all of them. What is the next step? What is the next step? What is the next step? So we know how long the activities take. But what else? What else? So when I talked about the pizza, I said, here's the activity. Put on cheese. That takes a minute. Put on the sauce. Takes 30 seconds. Make the dough. That takes 5 minutes. So what do I need though? What order? Okay. So oftentimes when we go through a project, we have to go to people and say, like, maybe this is done in the manufacturing area. We're going to have to ask the manufacturing department, how long is this prototype going to take? And we go to the marketing department and say, how long does this campaign take? And then we have to slot them in a certain order. So we work on that to get to something called a precedence relationship chart, okay? And a precedence relationship chart is kind of the building block for what we're going to do next, where we try to find out how fast we can get this project done. So every activity, A, B through J, and these would have names, obviously they have names in the previous, has an estimated completion time, and it has immediate predecessors. And the way you read this is A doesn't need to wait for anything to be done. A is like the start node, the start activity. B needs to wait on A to complete. C needs to wait for B to be done for it to start. D needs to wait on G. E needs to wait on D, and F needs to wait on A, G needs to wait on C and F to be complete. So these are like relationships, dependencies, if you will. Does that make sense? So this can't start until this one completes. C can't start until B is complete. So if we look at this, it kind of becomes, and I'm just going to skip ahead to the slide, it becomes a network diagram. So if I take that precedence relationship chart and I try to draw those relationships, I can create something called a network diagram. And that's what a lot of project scheduling software does. Does anyone use project scheduling software in the workplace? No one's ever used project? Anyone ever use Microsoft Project for anything? You use Microsoft Project? Okay. So Microsoft Project, there's an enterprise level and a desktop version. There's also a myriad of other project management software. But a lot of times you'll plug these in and there's options where you can say, show me a network representation. But this is a network representation. Remember we said B takes 15 days. It can't start until A is complete, so we see that. I think you remember we said G had to wait until C and F were complete. So that's why it's after that, okay? So when we get this situation, the first thing we want to do is we want to figure out the early start and early finish time for each activity. So Notice I called it early start and early finish, because each activity is going to have an early start, early finish, and each activity is going to have a late start, late finish. So we're going to have 2 start times and 2 finish times. So let's define what those are. The early start time is the earliest, best case scenario, that an activity can start. The early finish time is the earliest, best case scenario under normal circumstances, it can finish. So we want to figure that out first. And I'll show you this chart that tells you how to do it, but I think I'm going to show you how to do it first and then come back to the chart. So if we go to our network diagram, we always assume we start on day 0. So we go to any activity that has, no predecessors, nothing, that it can start right away, and that's A, and it gets a start of 0. Because it has a 90-day duration, its finish is day 9. Okay, so 0 to 9. Now we make a forward pass through the diagram. If this gets done at the beginning of day 90, when can this start? When can B start because it waits on A? 90. And when is it going to be over? 90 and 15, day 105. We can go forward that way, all the way through the network, so 90, this is a 25, 90 and 30. So we start figuring out the early start, early finish time for all these activities. 105, 110. Now we have a situation where G waits on 2 things. It waits on C and it waits on F. But G can't be done until both C and F are done. So when's the earliest G can start? 115, the maximum of the 2 predecessors' late finishes. So we can go here and then, no, 110 is not right, but 115 is. Sorry about that. Keep going through, 129, 149, 149, 170, 149, 177, 120, 165, 149, 194. Okay. So what we've done is we've made a forward pass through the network, and we've determined every node's earliest start and earliest finish. When can the project be done overall? When's the earliest the whole damn project is over? 194th, the biggest number there. 194 is the earliest finish for the project, and that's what we mean. Everything is done. Okay, so that wasn't too bad. We made a forward pass through the network. We figured out early start, early finish time for each of the nodes. We're going to do something a little different in the second step. We're going to figure out for each activity the latest start and the latest finish time, with the caveat that it can't affect that 194 days, right? 194 days is what we said, the earliest the whole project can get done. So we want to figure out the latest every activity can start and not impact that 194. Does this make sense? Okay. So what we do is we're going to move backwards. Instead of moving forward through the network, we're going to move backwards. And let's just go through it. So 194 is when the whole project can be done. So we start with the end activities that have nothing after them, and they all get a late start of the project completion. So 194, 194, 194. Their late finish is all going to be 194, 194, 194, because if they all finish at 194, hey, the project still got done at 194, right? And none of them, we didn't say they had to finish early, we just said everything has to be done by day 194. So 194 minus, what is that, 21 gives me 173. 194 minus 28 gives me 166. 194 minus 45 gives me 149. So now I start making a backward pass. So when is the latest D can finish without affecting the latest start time of the 3 nodes that wait on? When's the latest D can finish without affecting the late start of these 3 nodes? When's the latest? Well, 149, it needs to finish early, right? Because if it finishes at 173, it's going to delay this guy. So we take the minimum of all the late starts. So this one's going to be, I'm just going to cross it out, it's going to be 149, subtract the 20, we get 129. Keep working our way back. Well, D only waits on G, so we go back and that's still going to be 115, 129. If we look at, okay, C and F both need, this one. So 119, 149. If we look at, we'll go back to the beginning. Okay, so if we look at J, okay, if we look back at J, well, this J waits on, the latest J can start as 149, so the latest I can finish is 149. Keep working our way back. The latest G can start as 115, so the latest C or F can finish because they both are predecessors for G is 115, 115. We subtract out their duration, 5, we subtract out duration, 25, and we work our way back. Okay, so what does that tell us? So now for every activity, we have 2 start times and we have 2 finish times. An early start and an early finish. So let's look at activity C, for example. What's the difference between the late start and late finish and the early finish, or the late finish and the early start? 5 days, okay? What we call that difference is slack. Okay, what that means is this activity C, it can be delayed 5 days and not impact that 194, right? It can actually start at 110 instead of 105, and it won't impact that 194. It has 5 days of slack, sometimes referred to as surplus. Okay. Let's look at another one. Let's look at activity E. What's the amount of slack that activity E has? What's that? 3. What's the latest it can finish? What's the latest it can start? What's the late finish and the early? The early finish is 170, and the late finish is 194. 24. That's 24 days of slack. How about activity G? What slack does it have? What do you say? 0, right. How about F? Right. How about A? Answer is none, right? Right, so think about this. We have activities that have slack. This one has 5 days. This one has 5 days. But we have activities that have no wiggle room, right? 0 slack. If we look, you guys identify the activities in that path that have 0 slack? What are the activities? A, F, G, D, and J. You know what we call that path in the project? Some of you might have heard this path. Yeah? Critical path. It's called the critical path, right? Every project has what we call a critical path. It is the longest path through the network. It is the path of activities that have 0 slack. And if we summed up 90, 25, 14, 20, and 45, some of you may have done that in your head, guess what those activities sum to? 194. Okay, so how can I use that information as a project manager? So I now know, I know the project can be done in 194 days. I can tell my boss, expected duration of this project is 194 days. But how can I use this information, slack, critical path, as a project manager to try to meet that expectation of 194 days? How can I use this information? Come on. Damon?
You can put your best people on the critical path that won't be delayed.
So a couple things I can do is if I'm the project manager, I realize that a delay of 1 day in F is going to delay the whole damn project 1 day, right? So A, I'm going to watch that project like a hawk, right? I'm going to make sure it's that activity like a hawk. Maybe I'll put my best people on it. Maybe I'll put extra manpower on it. And where, if I'm going to put extra manpower on it, where might I pull extra manpower from? Ones with Slack. So doesn't that make sense? Like, if I know, and sometimes when people think critical path, they think of activities that are like the most critical. When you think of like, pouring the foundation is very critical. But it might not be a critical path activity. It doesn't mean it's an important task. It means that if it's delayed, it's going to hold up the whole damn project, right? That's more so what it means. Like, the example they always use is when they built Disney's, what's the one with like the animals? What's it called? Okay, when they built Animal Kingdom, the task that was on the critical path was the planting of like the exotic grass they have. Why was that on the critical path? Because that didn't affect my experience there. I had an awful Disney experience, by the way. But overrated, I think. Happiest place on earth, my ass. I had like heat stroke there carrying my son in 104-degree temperature. Oh, it's awful. But anyway, planting grass was on the critical path. Why? It takes long. Yeah, because it takes a long time, right? And they said that has to be completed for the project, but that was a long activity, maybe 18 months or something like that, or 2 years, I don't know. But that was a critical path activity. So it doesn't necessarily mean it's the most important. So a couple things, and I kind of said this already. Activity start time and completion time may be delayed by planned reasons as well as unforeseen reasons, right? Sometimes it just happens, and we want to absorb this. Some of these delays may affect the overall completion date. To learn about the effects of these delays, we calculate the slack time and form the critical path. That's what we're doing here. Slack time we can get one of two ways. We can take the late start minus the early start, or the late finish minus the early finish. I don't know if you noticed that. Doing that subtraction leads to the same thing. The critical path activities must be rigidly scheduled. Those are the things we watch very closely, because if they're delayed, it's going to delay the overall project. The critical path is a set of activities that have no slack, connecting the start node with the finish node. The critical activities with zero slack, form at least one critical path in the network. And the critical path is the longest path, I think I said that. And the sum of the completion times for those activities is equal to minimal completion time of the project. That is our critical path. And if you use something like Microsoft Project, it actually does that for you. It'll actually say, it usually makes those activities red, right? It depends how you look at it, but they're red because it tells you as the project manager, hey, these are critical path activities. This is the longest path through the network. And truthfully, a lot of times, the way we, so that's the critical path. So how we use this, okay? We observe different types of delays or things we slow down, single delays or multiple delays. A delay of a certain amount in a critical activity causes the entire project to be delayed by that same amount. So if we delay activity A 5 days, the whole project's going to be delayed 5 days. It's a critical path activity. Whatever we delay, it adds right on. A delay of a certain amount in a non-critical activity will delay the project. The amount of delay exceeds the slack. So, for example, let's say activity C, I can't remember what it had, but say it had 5 days of slack, and I delay it 3 days. What do you think happens to the project? Overall, nothing. We absorb it. But if I have 5 days of slack and I delay that activity 6 days, what do you think happens to the project? 1 day, right? We can absorb 5 of those days, but not the extra one, and it gets compiled on. Now, the issue we have kind of gets a little trickier if we have multiple delays on multiple activities. So these are some scenarios. Multiple delays of non-critical activities, but the activities are on different paths through the network. So if we delay activity I less than its slack time, and activity E less than its slack time, what do you think happens to the project? Because they're not on the same path, what do you think happens to the project? it's fine, right? We can absorb them independently. There's no compounding effect. So the project completion is not delayed. And by the way, does anyone know what this is? What this kind of representation of a project is? It is. It's a Gantt chart. Okay, so if you use Microsoft Project, it shows that. So you have the activities over here, and then you have bars, and you have milestones, or like diamonds, and you have dependencies, which might be little arrows. But that's a classic way to represent a project. Excel doesn't do a great job with the Gantt chart. That's one of the things it doesn't do too well. So we kind of in this class. Multiple delays of non-critical activities. Activities are on the same path, but they're separated by critical path activities. So B, we delay by less than its slack time. E, we delay by less than its slack time. And they're on the same path, but there's a critical path activity between them. What do you think is the effect there? It's fine, you're right. There's no delay because, as soon as we get to G, we're back in sync, right? We're back in sync. So we absorbed it here, maybe we're a little bit, but hey, we're back in sync in G, so, it's like separate delays. So it's like a separate single delay. Now the problem comes in if the activities are on the same path, but there's no critical activity separating them, like B and C both get delayed by less than their slack time. There is like a compounding effect. Okay, there is. So we have to be aware of those types of delays. So here's what we're going to do for /break/exercise is I would like you, we're going to do one manually here, and then I'll show you how we're going to do it with Excel. Under Chapter 5, it says Sample Precedence Relationship Chart. And I built this today. So I would like you to look at that. I would like you to make a network diagram, go through it, figure out the early start, early finish first, and then the late start, late finish of each of those activities. Okay, so make a network diagram, and then figure out those items. Okay, so first thing we want to do is build our network. So I believe I have that represented up above here. So B weights on A, C weights on A, D weights on both B and C, E weights on D, F weights on C, and G weights on E, and H weights on E. And hopefully I have the duration. So the first thing we want to do is we want to do the forward pass, which is the easier one. So A gets a start time of 0, duration 4 is 4. So everything after it has an early start of 4, add the duration 4 and 8, 4 and 9. D needs to start, or earliest it can start is the max of all the early finish. So if we look at 9, we look at 8. The max is 9, so 9 plus 10 is 19. 8 plus 10 is 18. We work our way through. And the earliest all the projects are finished is 37. Okay, so G finishes 27, 37. 37 becomes the latest the whole project can be done. So that's our baseline. So our backward pass, where we start is we look at the nodes that have no successors. All the finished nodes. And those are G, H, and F respectively. There's nothing after G, H, and F. So they all get a late finish of 37, right? So 37 minus 10 is 27, 37 minus 5 is 32, 37 minus 10 is 27, and then we work our way back. So the latest that these two can start is 27 and 32, so the latest E can finish, because G weights on E and H weights on E, is the minimum. So that's where the 27 comes from. 27 minus 8 is 19. Keep working our way back. There's only one here, so it's 19.9. This is 37.27. Now C weights, C has successors of both D and F. D needs to start at 9, and F needs to start at 27. So the minimum of those is 9. 9 minus 5 is 4. Keep working our way back. And we have all the late start, early start for all these nodes. And if I look at this, it does look like I have one critical path. A, B, D, E, G. If I add those up, 4 plus 5 is 9, plus 10 is 19, plus 8 is 27, plus 10 is 37. The durations of those activities do indeed add to 37. If I look at slack, so C has slack of 1 day, 5 minus 4 is 1, 9 minus 8 is 1. It looks like F has a whole lot of slack. It has slack of 19 days. And it looks like H also has slack of 5 days. So that is, my early start, early finish, late start, late finish for this project. Now, what I wanted to show you is the way this is represented in a lot of network diagrams with various software is you'll see like a square, and it'll have four corners of that square, and they put early start here, early finish here, late start, late finish, and then they'll put the name of the activity and perhaps the duration here, like 10 days, something like that. So a lot of times you'll see it shown like that in various software. Now, that is kind of the old school, ugly way to solve that. And I alluded to several times that we also have software to do that, like things like Microsoft Project. But what it's using behind the scenes, what it's using behind the scenes is, believe it or not, it's using constrained optimization models. And what we're actually doing when we do the early start, early finish is we're minimizing the project completion time. And if you think about it, all those relationships really are our constraints. For example, D cannot start until G finishes. So G starts and finishes. So all those things become constraints in the model, and I'm trying to decide where to start. So what we're going to do, do I have Excel up anymore? Doesn't look like I do. But if we go to Blackboard, I want to show you how we're going to solve this with Excel. And it's using constrained optimization models behind the scenes. But there is something called a PERT CPM template. So don't use the one that comes with the book. It was wrong, so I fixed it. So use the one that's on Blackboard. It says PERT CPM template. And when it comes up, it should say my PERT CPM template. And it looks something like this. And I'm going to take that precedence relationship chart we just did, and I'm going to copy that over here so I have it in one place. So what we do is in column A, we can write the name of the activity. So I'm just going to write start. I could have wrote A in there. And then it automatically assigns it like a letter prefix just sequentially. So it gives it the node of A. And just for the rest, I'm going to be lazy. I'm going to say B, C, D, E, F, G, and H. But I could have written in there, planning and prototyping and manufacturing. And it would assign those A, B, C, D, and H. Now what I'd like to do is I am saying for this example that these things are known with certainty. So this is going to take 4 days, 5 days, 4 days, 10 days. So I'm going to put that in column F. So 4 5, 4, 10, 8, 10, 10, and 5. And then I need to tell it about my relationship. So the way I enter this is kind of opposite of the way it's in the chart. I want to say B waits on A. C waits on A. Now D waits on both B and C, so I have to put it in there twice. I have to say D waits on B and D waits on C. You guys see what I'm doing there? So I have to enter it in twice because it all gets entered as a constraint. E waits on D, F waits on C, G waits on E, and H waits on E. Now what you're going to like, once we have this entered in, what you're going to like a lot is if I go to data, someone turned off my solver. You're going to see that the solver parameters are already installed in here for you. So if I click solve, I don't have to change anything. Don't change anything, just like the network templates. I click solve. It says solver found a solution. Great. Now nothing changed on this sheet, you'll notice. Now you'll notice it goes from IJK to U. No alphabet goes that way. So what you'll see is if I highlight between K and U, I do that, I'm not sure why my mouse isn't reacting, and I right click and go unhide. What it really did is there's some hidden cells in there that it kind of primed. It's like a two-step process. So you see it figured out the early start, early finish for all those nodes. You guys see all those nodes are in here. But I really want this in a better format, so I don't need to unhide that. I just wanted to show you that's what it was doing. So if I undo it, it'll hide it. And if I go to the PERT output tab, so the next worksheet, and I solve again, you'll see it populates this tab with the same answer that we did when we did it manually. So the mean, or the earliest the project can be done, is 37 days. The critical path is the ones with the asterisk, which is A, B, D, E, and G. And it also has the early start, early finish, and calculates out the slack time for us. So that did what we did manually, a lot better, a lot quicker. And project management software, by the way, is geared to do that. Without even this, it's better, it's more productive, it's better. When I worked for M&T Bank, I can still remember when we installed our first enterprise project management software. People didn't understand why are there 2 start dates, why are there 2 finish dates, because they didn't understand what early start, early finish, and late start, late finish. They just, starts are a start, okay? So you guys understand that part, and that's called, I think I kind of left that out. There were 2 kind of project management things that kind of came together to become one thing. One was called Program Evaluation Review Technique. It's called PERT. Where does that sound like it came from? Program Evaluation Review Technique. Sounds kind of military-ish to me, right? So it came out of like World War II when they were trying to move things about men and material all around the world as efficiently as possible. And the other one is CPM. And CPM stands for Critical Path Method. So they were like 2 different branches, kind of 2 different approaches to project scheduling, and they came together called like PERT CPM to become like the one best way. So that's what we're doing today. That's why it's called my new PERT CPM template. That's Program Evaluation Review Technique, Critical Path Method. Now I want to go back to this. Okay, let's go back to our PERT input. And let's look at the activity times. Now, when I say, for example, who lives far away? Who lives the close to me? Anyone State College? Where you live? State College? All right, can someone beat State College? I think State College got it. Okay. So, Jill, how long is it going to take you to drive home tonight?
An hour and 10 minutes.
Okay, 70 minutes is your estimate. Now, is it always, every day, going to be 70 minutes? No. Okay, so what we are doing right now assumes certainty. Like it's going to take you 4 days or 5 days or 70 minutes. But we want to add variability to that. Okay, we want to add some variability to that because we realize, that when we say we're going to do something, there is variability. Sometimes we get it done faster. Sometimes it takes a little longer. When you drive to State College, sometimes it takes you exactly 70 minutes. But some days maybe it takes you 80. Some days maybe 60 minutes, right? Maybe 70 minutes is best case scenario. Worst case scenario is 120 minutes. All right. So what we want to do is add some volatility to this thing. So the way we can do that, I'm going to go to the docket camera here, is by using the attributes of the normal curve. So when you saw the column I entered in, it looked like this. What does that symbol mean? What is that symbol? Especially people that took me for like 6 credits of statistics should answer this question. Huh?
One of those standard deviations.
Well,
I'll keep guessing.
you didn't take me for statistics. What is that symbol? Tara. Lance? What's that symbol? Don't say you.
Standard deviation.
No. What's the other one, Lance?
Mean.
All right, it is the mean, right? Mean means average. It's called mu, right? Mu is average. It's mu. So we entered, if you remember, what we entered into was the mu column. See, mu, okay, well, that was the average, but the symbol next to that is what, Lance? Now you can get to the answer to that. What is it? That is the standard deviation. So when we look at a normally distributed distribution, it is bell-shaped, the natural distribution. We have the mean in the middle, and the standard deviation controls the spread of it, okay? And bigger standard deviations mean more spread out, smaller standard deviations mean less spread out. And about how many standard deviations over does this curve go? And in fact, the empirical rule tells us 99.7% of all observations are within how many standard deviations of the mean? Do you guys remember this? That's asking a lot, probably. Is that fair one? Go ahead.
One on positive and one negative.
Okay, if you go over, say, let's do IQ, so we can visualize this. Average IQ is 100. So if you're over 100, you're above average. The standard deviation of IQ is 15. So what that means, the empirical rule tells us, if we go over 15 this way, that's 115, and 15 that way, which is 85, roughly 68% of the entire population is between 85 and 115. That's one standard deviation over. 115 over. If we go over 2 standard deviations, that would be 130 to 70, approximately 95%, almost 95% of the populations are within 2 standard deviations of the mean. Do you guys remember this at all? And if we go over 3 standard deviations, so that'd be like 145 to 55, that's going to capture almost all, or 99.7% of the population, right? So that is how standard deviation works. And this symbol is what? That standard deviation symbol is what? What is the symbol? Not mu, but, come on, some of you are fraternities or sororities. So. Sigma, okay, sigma. Anyone ever hear of 6 Sigma? Is anyone 6 Sigma certified? You are? Okay. So you should know that somewhere.
Yeah, I do.
All right.
Just,
So what is 6 Sigma certification?
it's trying to get a process as linear as possible.
Okay, so 6 Sigma certification, the name 6 Sigma certification comes from you do a process with such quality that the error rate is like so rare that it's like 6 standard deviations outside of normal, right? It's like 3.4 errors or something like that per million replications. So that's what it's like a process to say, you know, the error is so rare that it's 6 standard deviations outside of normal. So anyways, where we're going with this is when we build in a mean, and let's go down to, let's go to our thing, and let's say we give everything a standard deviation of 1 day. Okay. So what I've done is I've built volatility into this. So I say this activity is going to be done typically for 5 days is the average, but the odds that it's done between 4 days and 6 days is 68%. The odds that it's done between 3 days and 7 days is 95%. 2 days and 8 days is 99.7. So I built volatility into that. So what? Well, what's useful about that is I'm going to resolve with those new standard deviations in there. Let's click OK. I'm going to go over here and I'm going to resolve. Okay. And we still see 37 days is the average completion time. And we still see the same stuff down here for AB, this is the same critical path. But now our overall project, because of the volatility of all the tasks in the tasks that make up the project, our overall project has a mean of 37 days, but it also has a standard deviation of, we'll call that 2.2. So 37 days with a standard deviation of 2.2 days. So what good is that? Why might we use that? What's the odds, if that's the distribution, what's the odds that this project is going to take longer than 37 days? Because 37 is right in the middle. 50%, what's the odds it's going to be done in under 37 days? 50%. So if my boss says to me, you know, what's the odds it's going to be done in under 32 days? You know, I can say, well, you know, pretty unlikely. Okay, and actually, we don't have to figure that out. There's an equation to do so, but that's also built into the template. So if I put in probability complete before, and in this case, we'll just use my first example. What's the odds that it's done before 37 days? It's 50%. If maybe 40 days is like a drop dead deadline, we can put in 40 and it says, hey, there's a 91% chance you're going to meet that deadline. But if my boss says something crazy like I want this done in 30 days, I'm going to put in 30 and say, hey, it's not likely, right? There's an 8 in 10,000 chance that could happen. So it's not very likely as the project is currently configured. What if I wanted to know what's the odds that this project takes longer than 35 days? How would I get that using this tool? So if I put in 35, it gives me, let's just call that 18% chance that it's going to be done under 35 days. So what's the odds it's going to be done longer than 35 days? 1 minus 18% or 82%, right? 80, right? Yeah, 82%, okay? Now, how many of you think in terms of standard deviation? Yeah, maybe there could be people that do. Okay, there are likely people that do think that way, but most of us do not. Okay, so to try to capture that volatility, but in terms of humanistic terms, people came up with, and this is part of the PERT CPM approach, something called, and this is useful in a lot of things, it's called the 3-time estimate approach, and we can also use it for cost estimation. So we have 3 things. We have A, M, and B, where A is best case scenario. I can't write scenario. M is most likely, and B is worst case. So all of us can kind of talk in that situation, right? We can all say, you know, best average, I drive home to State College in 70 minutes, right? That's my average. You know, worst case, and I know there's worst case, but a worst case on just a general day maybe is 85 minutes. And best case scenario, maybe 65 minutes, right? So you can think like that. You don't have to think in standard deviation. But what we do is we use those. So let's say, I'm going to make this easy on myself. Let's say best case scenario is 10 days, most likely is 20 days, and worst case is 30. We calculate an average by using this formula. It's a weighted average. We take A plus 4M plus B divided by 6. So that's how we figure out the average. And we don't have to figure that out. I just want to show that to you. But it's a weighted average where it's giving 1/6 of the weight to the best case scenario, 1/6 of the weight to the worst case scenario, and 2/3 of the weight to the most likely scenario. So in this case, it would be, oh, it's going to come out to 20 because of the way I did it. But it's still going to be 20. And then the standard deviation is B minus A, the worst case scenario, minus the best case scenario divided by 6. 30 minus 10 is 20 divided by 6. Gives me 3.333. Okay, so that would be the best case. So then it uses that as the mean and that as the standard deviation for that task, right? It tries to take the way we think and put it in terms of mean and standard deviation, which allows us to do, probability better. And the same thing happens with cost estimates. So a lot of times people use a three cost estimate, and that's what the method they're using. They're saying, give me, the best case scenario for the cost, the worst case, and the most likely, and it's a weighted average. It uses 4/6 of the most likely, 1/6 of the best case, and 1/6 of the worst case. And that's an approach that's used a lot in the business world, not just for project management. So we're going to go back to our example. And let's just try to, I'm going to copy that mean column into the M column. This might screw things up. And let's just go like 2, 3, 2, 8, 6, 8, 6, 4. 6, 7, 6, 12, 10, 12. So I try to keep the mean the same, so it comes out to 37. I'm not sure I did, but that's the most likely case. That's the best case, and that's the worst case. So instead of adding in the variability with the mean and standard deviation, I'm using a 3-time estimate approach. I'm going to go to data, I'm going to solve, keep it. I'm going to go to PERT output, I'm going to solve, it actually already is. And we see now we have a mean of 37 because I kept kind of the most likely the same, and I went the same weight over for the best case and worst case scenario with a standard deviation of 1.8. So this can be useful to me, right? Because I can, if I build in variability in my project, then I can start answering questions. If my manager asks me, what's the best case, what's the odds that I get done? It's not 35 days or 37 days. 50% of the time we'll get done in 37 days. But if you want a date that I'm 95% certain I'll be done within, well, then I'd have to give you maybe 40 days or 41 days or 42 days. Does that make sense? Because a lot of times in the business world, we speak in absolutes, but we realize, things don't happen according to absolutes. There's no certainty in that. We want to build in that uncertainty, that variability, something called risk. Some are more risky than others. Make sense? Okay. Let's move forward. I already went through this. This is in the slides, but I think I went through this. And there's a bunch of stuff in here about Z-curves, which if you took me for stats, you remember that, but I'm not going to drag you through that in MBA505, so you don't have to worry about that. And we're going to skip ahead to section 510. Okay, so what are our options? We set this up, and the project is done according to, we went through the critical path method, and maybe it's done in 100 days, and that's not what we want, right? That's not what we want, 100 days. So we want to reduce the project completion time, and it's called project compression techniques. How can we do that? How can we compress a project? How can we compress, get something done faster? Okay. One way we can do that is by spending more money. In the world of project management, this doesn't sound good, but we call that crashing a project. Okay? That's a project compression technique, reducing the duration. It's called crashing, adding money or men, material, whatever it might be, but it all comes down to money, right? People come down to money, material comes down to money. So by adding more money, we can reduce completion. Okay, that's called crashing. Now, not every activity can be crashed, right? The project management joke or saying, no matter how many women you assign to birthing a baby, it still takes 9 months, right? You can't add, it still takes 9 months. You can't crash that any further. So, not every activity can be crashed. Another project compression technique is something called fast tracking. You ever hear of fast tracking? It's fast tracking. You ever hear put on fast track? No? That's a phrase that's brand new to all of you? I hardly think so. But what is fast tracking? Fast tracking is, I guess a good example of that is if you ever watch that show, I never really watch it, but Extreme Home Makeover or Home Takeover, where they come in and they make a home, like a different home in like 3 days or 5 days. You guys know what I'm talking about? Well, what they do in those situations is, usually when you do a project like that, you have dependencies, like, hey, you don't lay the carpet until after the painting is complete, right? And those are called discretionary dependencies, meaning they don't, you don't have to do that. So when we do fast tracking, we say, let's get rid of those dependencies. Let's say, let's lay carpet and paint at the same damn time, right? So fast tracking is a method of saying, things that were done sequentially, maybe, if they can be done in parallel with one another at the same time, let's do them in parallel, right? And that's kind of when you see those shows, that's what they're doing. They're doing a lot of things that normally, has some kind of hierarchy to it at the same time. So what we do with crashing an activity, and there's some templates on this, but they're terrible templates. So I just kind of want to talk about it a little bit. When we talk about crashing activity, there's something in project management called the iron triangle. What is the iron triangle? You ever hear of that? The iron triangle in project management? No? Sometimes called the scope triangle. There's 3 main things that affects your project, okay? It is cost, terrible S, time, and scope. And the reason it's called the iron triangle is because when you look at a project, if I want to reduce the time, right, if I want to reduce the time, compress it, what are my options? What are my options? I can spend more money, increase the cost, or reduce the scope, like maybe not build as much or not do as much, right? If I want to reduce the cost, what can I do? I take longer, right? Or maybe I can do less. Does that make sense? So same thing with scope. If I want to do more, well, it's going to take more time, more cost. So those two, that's why they call it the scope triangle. Sometimes they call it the iron triangle, because things are related together. And if you think about it, when we're talking about what we've been talking about, like constrained optimization models, when we look at things, here's the other piece of paper. We have been saying we can decide this, and we have an objective function here and constraints here. Okay, so this is like we're going to decide when we crash a project how to spend our money, like where to spend our money to crash this project. So we're going to spend more money. We can think of it two ways. If the deadline is the thing we have to meet, where does that go? Is that in the objective or is that in the constraints? If the deadline is a drop-dead deadline, is that a constraint or an objective? It's a constraint. The things we have to have go in as constraints. So this would be, the deadline would be something we have to have, and our objective would be to minimize the cost but still meet the deadline. Okay. The other way we can crash a project, if we say we can only spend this much additional money, that would go where? If we only have an extra $50,000 to spend, where would that go? That would go in the constraints, so we can only spend $50K, and our objective would be, well, do your best, minimize the time with that $50K. Does that make sense? So there are some things, the templates that your book uses for this aren't very good. But those are the two approaches we can use when we crash a project. We can say, we have to meet this deadline. For example, how many people, I used to be like the youngest person in my MBA class, now I'm the oldest. Truth, that's true. Like 15 years ago, when I first started teaching, I was like younger than most MBA students. Now I'm older than most MBA students. But who remembers the Y2K issue? Okay. That was what? That would be an example of we have to get this done, and what is the constraint part?
5 years and
Deadline, December 31st, December 31st, 1999. So what a lot of, and I was an expert at some software for banks called M&I. So I got a lot of money during 1998 to 2000. I made more than I should have ever made. Because I was an expert at something and they didn't care. They needed to make that deadline, so they spent a lot of money on resources. That was an example where the deadline was something we had to have. Now, if we just say, hey, we have some money that we can add to this project, what's the best way to do it? That would be an example of minimizing time, but the deadline or the constraint is the extra money. So where do you think, before we look at the slides, where do you think when we crash an activity, where we want to put that money? Just knowing what you know about activities, where do you want to put that money? Where would be the first place you'd look to put that money? Very good. Okay, so think about it. When we talked about it, we said what? We said that if we reduce, these slack activities have wiggle room, so why would we spend that money there? So the first place we look is the critical path. And not only that, we need to look at the marginal cost of reducing an activity. So a day is a day no matter what activity you're talking about. A day is worth a day. But if there's an activity that you can crash, they're both on the critical path, they're both equal in weight as far as what it buys you in the project. But one costs $1,000 to crash a day, and one costs $500 to crash a day, where are you going to spend that money? The $500 per day, right? So the way this works, and like I said, we're not going to really use the slides for this, but I want to understand what's going on. When we do a crashing mechanism, every activity has a normal completion time, T sub n. Every activity has a crash completion time. Sometimes these are the same, right? Like, the bearing a child, right? You can't crash it any further. It takes 9 months. So sometimes these are the same, sometimes they aren't, right? 10 days, maybe 5 days. Every activity has a normal cost, C sub n, that if you spend that amount of money, you'll get it done in the normal time. And it also has a C sub C, the crash cost, and that is to get the activity done in T sub C, the crash time. And what we do, okay, is we look at every activity, and for example, we use this activity. It can be done normally for $2,000 and take 20 days. The most we can crash it is down to 12 days, but it's going to take an additional $2,400. So if you think about that, we bought ourselves 8 days. How much did those 8 days cost us? $2,400. So marginally, each day cost us $2,400. But we bought ourselves 8 days. Each day cost $300 per day, right? That's the marginal crash cost, right? So that is, and we use the linearity assumption, so we assume that, every day. So we look at the marginal cost, and then we crash the activities that are the cheapest, right? And there's templates that are in your book, but they're awful, they're kludgy, they're not built very well. I want you to understand the concept of compression techniques. I want you to understand the concept of crashing versus fast tracking, but we're not going to do the projects related to this activity because it's not done well in Excel. Okay. Now this was just a kind of a subset of project management. As I said, the MBA. I think Mr. Tompkins is actually teaching a course on project management in the spring, if you're interested in it. I think it's going to be an online class, so if you're interested in project management. I'm a PMP. You guys know what PMP stands for? It's kind of an unfortunate acronym because it kind of sounds like pimp, but PMP stands for Project Management Professional. There is an institute called the Project Management Institute, and they put out something called the PMBOK. It's the Project Management, I like this term, Project Management Body of Knowledge. Isn't that a nice term for like a standards manual? So, and you can get that free, I think. You can find that free. But it talks about there's 10 knowledge areas for managing a project, like risk, quality, cost, time, HR, procurement. So if you think about it, the study of project management is a great field because it's truthfully the study of like getting things done, right? Getting something done, which is tantamount to why we're in business. So if you're interested in this a little bit, I think that would be a good course for you to take in the spring. So the last thing I want to do today is, I mentioned at the beginning of class, I mentioned our group project, which is due November 22nd. Is that before or after Thanksgiving? Week of?
Yeah.
So we're done before Thanksgiving. That's great. So I do want to push through. Does not seem right? Yeah, it's 14 weeks. Yeah, that's all we need is 14 weeks.
And our finals the week before that.
November 15th, yes. And what I want to talk about today is in the syllabus, I have information about the group project, and I kind of want to explain that today because you should start to think about that project. And now that we have some material under our belt, I think it will make more sense than when I explained it week one and you didn't know what I was talking about. Okay, so the final MBA level group application project. As part of the class, each student either individually as part of a 2 or 3 person team. Like I said, I'm fine with, I really don't want people doing it individually just because we have 30 in here. This is a big class. Typically MBA classes aren't this big. So I would say as part of a team, 2 to, I don't care, 5 would be fine. Okay, 2 to 5 person team. I'm fine with 2 to 5 person team. We'll complete an application project. So this isn't like a research paper. You're not going to go to the library and say, look at the literature review on sensitivity analysis. What I want you to do is take a technique or a model that we used in class, and I want you to apply that to something in your workplace, right? Some of you I know are like full-time students and maybe don't have a workplace. So what I would advise you to do is then get on a team with someone that has a workplace that would have access to, hey, a problem. And some of these things can be applied to personal issues as well, like not personal issues, but like personal projects, like, hey, I'm building a house or I'm planning a wedding, do a project management model. Those aren't usually great, but they can work. So it's not an academic research type of report, rather it's an application report focusing on the use of quantitative decision making. The topic must be approved by the instructor. And that's not like a formal approval. You just have to come up to me after a class, and I'll give you a little bit of time later in the class and say, this is what I want to do. Does this make sense? And I can say yes, and I can give you some insights on how I would attack that problem. Okay? What it should, most typically the report and presentation, so it's going to be a little report and presentation, and I'm not going to say like it has to be 10 pages long or 20 pages long or 30 pages long. I want you to determine, hey, how long does it need to be to convey the information that I convey? When your boss tells you to prepare something, she doesn't tell you it needs to be a 3-page, 1,000. She doesn't, right? That doesn't happen. That's a figment of education, which it is not, not applicable to what we're doing here. So it needs to be as long as it needs to be. Okay, and the format of it is what you would produce if you're presenting this to a decision maker in your organization, a board, your boss. You're trying to convince someone that here's the analysis I've done, here are the alternatives, here's my recommendation, and here's why, right? That's what I want you to do. So you can use, a network model, you can use any project management model, you can use, we're going to talk a little bit about queuing. Next week we talk about decision analysis. The week after we talk about forecasting. Almost everyone in a workplace forecasts something, sales, demand, the budget for next year. So it could be a forecasting model, it could be a staffing model, any of those things, anything we worked on. And in fact, it can go beyond what we worked on in the class. What I'm trying to get you to do is take some kind of work situation, work problem, apply a mathematical model to it, okay? Come up with some recommendations or a solution, and then talk about that. So application, description, setting, background. So what people mostly talk about there is, hey, I work for ABC Company. ABC Company produces these type of widgets. It's been in business since 1847. We have a situation where this doesn't run most efficiently because blah, blah, blah. So what I decided to do is I quantified that information and I put it in this model. The data I got from this model came from these sources. When I ran the model and solved it, here was the result I got. Based on that result, I'm going to make these suggestions, conclusions, suggestions for further study. I think it says 50 possible points. It's 35. I think that's wrong. So you'll do a presentation and a paper, and both of those things should be whatever would be appropriate for if you were, giving this to your boss or a board or something like that, but not real long because, like I said, we have 30 people. I'm trying to think. So, the one thing I wanted to say is sometimes people say, like they think, this is, as Dr. Miko taught me this must be, he wants it to be the be-all and end-all. So sometimes, though, you'll do this kind of analysis, and you'll come up with a solution. You'll say, you know what? I know the model says this, but I wasn't able to bake these 3 things in the model. And so this isn't a good solution, right? And say why it's not a good solution. Like say why, I tried this model, but it didn't work out. So the way we've been doing it, or the rule of thumb, makes more sense than this model. That's not going to offend me. That's real life. Management is part science and part art, and you need to know the difference between the two. The other thing I want to say is the hard part with actually applying this in the real world to real world applications in a lot of cases is what? That's a really hard part of this. Because this isn't the hard part when you do a book problem.
Knowing what to use.
Knowing what to use, that's important, you're right. That's also, those are the two things that students struggle with. They're like, I want to do this. Well, what data can you get? Like, how can you, if you want to forecast, well, how many past series and past data points can you get from your current workplace, right? And what model makes sense? And sometimes students use combinations of models, right? They maybe solve something and then put it in a forecast, or they do a queuing model and put it in a project management model. So, use something from this class to solve some kind of problem. All right. Any other questions? Any questions on that? All right. Oh, I didn't give you homework. So, homework. This is on page 312, 322 of your text. Number 1, number 4, number 7, and number 12. Do all those with Excel. Okay, do all those with the template that my new CPM Perk template is down on black. Okay, 4, 7. Have a good evening.
For the project?